Hello everyone, welcome. Today we're starting chapter 11, Infinite Sequence and Series. So let me start the class right away. In chapter 11, we primarily focus on series. We use power series to represent some of the important functions that arise in mathematics, engineering, physics. Later, we discuss the Taylor series, which you can use to develop a power series to represent the certain types of functions. The whole point of series is to understand the limit of its partial sums. First, we explore the sequence of numbers and the limit of the sequence. Later, we analyze various tests for the series convergence. In chapter 11, we cover the following: sequence, series, then integral test, comparison test, alternating series test, absolute conversion test, ratio test, root test. These all tests are for series, whether it converges or diverges. Power series and Taylor series. Now let me start sections 11.1, Infinite Sequence of Numbers. First definition: a sequence is an infinite order list of numbers such as a1, a2, a3, an, This list goes on forever, and we denote the sequence by an inside the curly bracket, and n goes to 1 to infinite, or simply an inside the curly bracket. Quick example: sequence n means n has a element 1, 2, 3, Sequence 1 over n means 1, 1 half, 1 third, Just put n equals to 1, n equals to 2, n equals to 3, and so on. And sequence 1 over 2 to the n is 1 over 2, 1 over 4, 1 over 8, Let me scroll down. Alternately, a sequence is real valued functions from natural number to real number, given by a of n equals to f of n, and we write an equals to a of n. So we can plot the terms of sequence using bullets and join them by a function having finitely many discontinuity. So here's 1, a1, 2, a2, 3, a3, and so on. Quick remark: a sequence follows a pattern, and the first few terms suggest that pattern. And there are three types of sequence with standard pattern: arithmetic sequence, geometric sequence, harmonic sequence. Arithmetic sequence, the formula to find the nth term is first terms plus n minus 1 times the common difference. So the pattern is here: each consecutive term differs by the common difference. For example, here's 3 minus 1 is 2, 5 minus 3 is 2, 7 minus 5 is 2, and so on. In geometric sequence, the formula to find the nth term is first terms times the common ratio to the power n minus 1. This r is the common ratio, which is the ratio of consecutive terms. For example, here 6 over 2 is 3, 18 over 6 is 3, 54 over 18 is 3, and so on. Harmonic sequence, it's a sequence whose terms are the reciprocal of the terms of the arithmetic sequence. So here is the arithmetic sequence, so take the reciprocal of each term, so 1 over 1, 1 over 3, 1 over 5, 1 over 7, and so on. So this is the harmonic sequence. Great, let's move on. Next definitions: limit of a sequence. A sequence an has the limit L, and write limit n goes to infinite an equals to L, or in short, an approaches to L if the terms of the sequence eventually approaches to L as n gets sufficiently large. L is the limit of a sequence, means that the sequence is convergent and in fact converges to the same number L. Else we say that the sequence is divergent. So now two fancy name here, convergent and divergent. Visualize. So this is the number L and these are the terms of the sequence, so that eventually converges to L. So here, this is the number L and these are the terms of the sequence. So we don't care finitely many, and then if we only care the tail of the sequence converges or not. So now it converges to L. So here the 1 over n sequence converges to 0. Great. Quick fact: the sequence r to the power n is convergent if r is between -1 and 1. That means if the absolute value of r is less than 1, else divergent for all other values of r. Example: the sequence 3 to the n times 7 to the power -n is convergent and in fact converges to 0, since the nth term is 3n over 7n, that is 3 over 7th outside power n, where common ratio is 3 over 7, which is less than 1, and this in fact converges to 0. Great. Now let's move on. Underlying function test. We go by UFT. Suppose function is continuous real value functions and f of n equals to an, an integer. Define the sequence an and limit x goes to infinite of fx equals to the number L. Then the limit of the terms of the sequence converges to L. Squeeze theorem for sequence. If you have three sequences an, bn, cn, and if an is dominated by bn, bn is dominated by cn for all n, and the limit of the smaller sequence and then the larger sequence converges to L, then the middle sequence must converge to the same limit L. In the picture is clear. Fact: if the limit of the absolute value of an is 0, then limit of the an also 0. Monotone sequence. Our sequence is called monotone if it is either increasing sequence or decreasing sequence. Quick idea: to show a sequence increasing, we show either one of the following. To show increasing, nth plus 1 term minus nth term is strictly positive, or we show the ratio of n plus 1th term over nth term is greater than 1, which is basically the same thing. Yeah, you just cross multiply and bring this n to the left, or assume function equals to a of n when x is greater than 1 using underlying function test, then show that the derivative is positive to show the sequence is increasing. Similarly, for the decreasing case, bounded sequence. A sequence is called bounded if either there are two numbers m and m such that the terms of the sequence are bounded below and above by those numbers. Great. Now we have another useful formula, means theorems. Monotone convergent test for sequence. Every bounded monotonic sequence is convergent. Great. So let's begin the solving some of the problems. So first example, list the first 5 terms of the sequence 2 to the n over 2n plus 1. So just put n equals to 1, n equals to 2, n equals to 3, n equals to 4, and so on. So here our solution is sequence equals to, put n equals to 1, so 2 to the power 1 over n times 1, sorry, n equals to 1, so 2 over 2 plus 1, 3, so 2 over 3. Similarly, the second term, put n equals to 2, so 2 is square over 2 times 2 plus 1, so 4 over 5, and so on. Example 2, look for a pattern. So find a formula for the general term, means nth term of the sequence. The sequence is given in a listed form here, so 1, 1/3, 1/5, 1/7, 1/9, and the part B, 5, 8, 11, 14, 17, So let's begin the solution. Part A, here the first term is 1, so we can write 1 equals to 1 over 1, and we can write the 1 in denominator equals to 2 times 1 minus 1. We are searching for the pattern here. If the first term doesn't give us any pattern, then we can find out from the second term or from the third term, and so on. That's the idea. So the second term here is 1 over 3, so we can rewrite 3 as 2 times 2 minus 1. Third term is 1 over 5. We can rewrite the 5 as 1 in the numerator as it is, 1 over 2 times 3 minus 1, That means the nth term is 1 over 2 times n minus 1. So now this is the nth term. Great. Similarly in the B, it seems to me it's a arithmetic sequence. So let's see, the first term is 5, and then the common difference here is 3 from first and second term. Second and third is 3, third and fourth is 3. Then our A2 is 8, so 8 we can write down the first terms plus the common difference. A3 is 11, which you can write down 8 plus 3, or 5 plus 3 times 3 minus 1, because I'm looking for the formula for the arithmetic sequence, and we know the nth term equals to first term plus n minus 1 times the common difference. So now we're using the pattern now. So an equals to first terms plus common difference times the n minus 1. So an equals to then 3n plus 2. So this is the nth term of this given sequence. Awesome. Now let's move on. Now let's do example 3. Determine whether the given sequence n square plus 3 over 2n square plus n converges or diverges. So to show the sequence converges, now we use the definitions. We take a limit of the nth term, whether it gives me the real number L or not. So that's the idea. So here nth term equals to n square plus 3 over 2n square plus n divided by n square numerator and the denominator. So then this gives us 1 plus 3 over n square over 2 plus 1 over n. Then take the limit. So limit n goes to infinite of an equals to limit n goes to infinite. So 1 plus 3 over n square, 2 plus 1 over n. And when you take a limit n goes to infinite, this ratio goes to 0, this ratio goes to 0, so we have 1 over 2 left. So we have a real numbers. That means by definition the given sequence converges. Great. Similarly, let's take example 4. Determine whether the sequence 3 times radical n over radical n plus 2 converges or diverges. Begin with the solutions. Here's the nth term. An equals to 3 times radical n over radical n plus 2. Then let's factor the radical n out from the denominator and cancel the numerator. So we take radical n outside in the denominator, so this gives me 1 plus 2 over radical n, and we cancel the radical n. The next step, this is 3 over 1 plus 2 over radical n, and take the limit as n goes to infinite. This 2 over radical n goes to 0, so we have 3 over n, which is 3. So by definition the sequence converges. Awesome. Similarly, let's do example 5. Determine whether the sequence 5 to the power n minus 3 over 2 times 5 to the power n converges or diverges. Solutions. So let's do underlying function test for this particular example. So let fx equals to 5x minus 3 over 2 times 5 to the x. Then take the limit of the functions as x goes to infinite. So that means take limit x goes to infinite of this right hand side. So here when x goes to infinite, this term goes to infinite and this term goes to infinite. So that means infinite over infinite. This is the indeterminate form. We can apply the L'Hopital's. So using L'Hopital's, this equals to limit x goes to infinite when you take the derivative of numerator over derivative of denominator. So the derivative of 5 to the x is 5 to the x natural log of 5, and minus the derivative of 3 is 0. We don't need to write the 0. Similarly in the denominator, so 2 as it is, the derivative of 5 to the power x is 5 to the power x times natural log of 5. Now we can cancel here. So 5x cancel, natural log of 5 cancel. So we have 1 over 2 left. So that means this is the limit of our sequence also. So that means the given sequence converges. Great. Now let's do example 6. In example 6, there are 3 parts. So determine whether the following sequence converges or diverges. A, n factorial over 2 to the n. B, n factorial over n to the power n. C, n squared times e to the power negative n. So in part A, let's use the definitions. Let's take the limit of the nth term. So limit n goes to infinite of an equals to limit n goes to infinite of n factorial over 2 to the n. N factorial is n times n minus 1 times n minus 2 times times 3 times 2 times 1 over 2 to the power n is n many 2's. 2 times 2 times 2 times 2. In the next step, we have to do some small trick here. So copy the limit as it is, copy the 1 over 2 as it is, and then the inside the parenthesis I just copy down here. And the next step, limit as it is, 1/2 as it is. So this number is bigger than n over 2. I hope this makes sense to you all. Then the next step, take limit n goes to infinite of n over 4, so which goes to infinite. That means the sequence diverges. Awesome. Let's do example B. Here I'm going to use Squeeze Theorem. So our nth term is n factorial over n to the power n. So n factorial is again 1 times 2 times 3 times n minus 1 times n. So that means I'm just reading backwards here. Over n to the power n is n times n times n times n. So now here is another trick again. So for n greater than or equals to 2, so the first one is copy as it is. So let's replace the 2 by n, 3 by n, 4 by n. That means I am replacing the numerator by bigger number, the n here. So that means this is n, this is n over n, n over n, n over n, means all of these numbers are less than or equals to 1. I hope this makes sense to you all here. So these all ones are there. Then we take the limit. When n goes to infinite, this number goes to 0. So then we have the inequality here. Obviously this nth term is greater than 0, and our nth terms, and then this will be bound by 1 over n, and the 1 over n goes to 0 as n goes to infinite. Then by Squeeze Theorem, the middle sequence also goes to 0. So that's the reason here we have the limit of n factorial over n to the n is 0. That's why this sequence converges. Awesome. Similarly, let's do part C. Now the nth term is n square times e to the power negative n, which is same as n square over e to the n. Then for this one, let's use underlying function test. So let fx equals to x square over ex. So replace n by x. Then take the limit of our functions. Limit x goes to infinite, x square over e to the x. Then this is when x is infinite, that means infinite over infinite. E to the infinite is infinite. Then this is the indeterminate form. We use L'Hopital's. So using L'Hopital's, limit x tends to infinite. 2 to the x over e to the x. That means take a derivative of x square, which is 2x over derivative of ex is ex. Again, when you put x equals to infinite, this is infinite over infinite. Again, indeterminate form. Use L'Hopital's. This equals to, using L'Hopital's, derivative of 2x is 2, derivative of ex is ex. So we have 2 over ex, then take the limit. When x goes to infinite, 2 over infinite equals to 0. So that means the function converges, means the corresponding sequence converges to that number 0. Great. Let's do number 7. Determine whether the sequence due to the n over n factorial converges or diverges. So let's use this times the monotone conversion test. Here, our nth term is 2 to the power n over n factorial. Then let's see the ratio of the n plus 1 term over nth term. So then this is 2 to the power n plus 1 over n plus 1 factorial. That's the an plus 1 term. And that's the an term. And divide by 2 to the n over n factorial means I just flip it here. We know dividing is same as multiplying by its reciprocal. Then this turns out to be, we can rewrite n plus 1 factorial as n plus 1 times n factorial. Then n factorial cancels, so we have n plus 1 down there. And on the numerator, this 2 to the power n plus 1, we can rewrite as 2 to the n times 2. So the 2 to the n power cancels here, so we have only 2, then 2 over n plus 1. And this number is obviously less than 1 when n is greater than 1. So that means 2 over 2 plus 1 is 3. 2 over 4 plus 1. So this number is less than 1. So that means, let's cross multiply. An plus 1 is less than an. This goes to here. So that means n plus 1 term is smaller than the nth term. That means our sequence is decreasing. So sequence is decreasing, bounded by 0. So that means the sequence is monotone bounded sequence. Then by MCT, given sequence is convergent. Great. So we finish the sequence today. In the next class, we'll start the infinite series. Thank you.